All right, so now we're going to talk about the idea of collapses of a complex. And again, the reason for this is because it's going to be at least some examples of them are going to be related to this idea of deformation retracts of spaces. And as we know, it's like a deformation retract that keeps the homotopy type of the manifold the same, right? And so it doesn't affect certain topological invariants. Okay, so let's suppose that we have a geometric sort of D simplex. Okay, let's call that sigma, right? And then we consider this Hasse diagram. It's like corresponding to all of its faces. Of its system of faces. Okay, and then we also add the empty set to this, right? And if you recall, it's like the reason for adding the empty set is because then that really gives you this Hasse diagram. It's like of a simplex, then really actually has the structure of a hypercube. Okay, so now I want to remove, it's like a pair, right? So I want to remove pair. Let's call that beta 0. And beta 0 has to be contained in beta. Okay, and of course it's when you're talking about these faces, you can either think of them as abstract simplicial complexes in which the entries or the elements of the complex are really just sort of collections of points, if you will, right, or sets of points. And of course, either whether or not you think of this, it's like as it's like a set of vertices. It's like or as actual faces. It's like there is this again one-to-one correspondence, especially when you have a geometric D-simplex. Okay, and so you have to remove a pair which corresponds to removing a pair of faces. Okay. So I'm going to denote the faces corresponding to beta. It's like by taus. So tau 0 is a subface of tau. Okay. So what needs to happen then is that you want to do this in a way which preserves the simplicial complex structure. So if I remove this pair, it has to be that tau is the only proper coface of tau 0, right? So to preserve the sort of simplicial complex structure, right? What has to happen is that tau has to be the only remaining sort of proper coface of tau 0. Okay, so in any case, when you remove this, it's like this is what is referred to as an elementary collapse. Okay, so this, removing this pair, tau 0 contained in tau, well, tau 0 is a subface, or it's a face of tau, okay, is referred to as an elementary collapse. Okay, or a k plus 1 collapse, whereas you might expect k is the dimension of tau 0. All right, so I'm going to show how the collapse works, right? So let's just say you start with the solid pyramid, okay? And what you want to do is you want to collapse the pyramid. It's like with respect to one of the faces, okay? So what you do basically is the following, all right? So you know that if you choose one of these faces, then there's one vertex which is not included in that face, which is this point here. And the intuition, if you will, is that you want to somehow deflate this so that you pull everything back down to that vertex. So how do you go about doing this? So one way to sort of think about this is that you can look at this barycentric subdivision of that face, okay? Well, I guess technically speaking, it's like you would also have these pieces, right? But let's just sort of get rid of these, and let's just worry about taking the simplices you would have gotten by adding the barycenter, and then taking the faces of that 2 simplex, and then each of the faces gets appended with the barycenter. Okay, so you get this kind of nice decomposition. And then you can sort of imagine taking that point and pulling it back down, if you will. It's like to this vertex, it's like which wasn't included in that face. Okay, so it sort of just deflates in. And maybe it's a little bit easier to see this in 2 dimensions, right? So imagine now instead of that you have just a triangle. And again, I want to collapse this face down, right? And then this is the 2 simplex, and then this is the 1 simplex. I've added a point here, and then sort of, if you will, it's like sort of midway, it's like through the collapse, you would have something like this, if you will, right? And then eventually you get to a point where you just get those 2 pieces. Okay. So hopefully that sort of gives you the idea. It's like of what you're doing, right? So again, here it's like I look at the faces of this 2 simplex, which are just these 2 vertices, and I take that vertex and I add the barycenter. So this gives me one of these edges, and I do the same thing. This vertex added with the barycenter gives me this other edge, right? And I can sort of pull this, it's like barycenter back down to this point here, and I end up with this sort of continuous deformation retract, if you will. It's like of this object down to this piece. So this gives you sort of a very clear sense in which how this idea of of collapse, right, is related to sort of, deformation retracts, if you will. Okay. All right. So the net effect of this is that you can go from, again, the solid. So this is the solid pyramid or tetrahedron, right, to something where now you just have the 3 of the 4 faces. It's like of the pyramid, right? Okay, so there's just this face, and this face is like a cone. Okay, and then you can do something like this, right, to collapse each of the 2 faces. Okay, so let me try to sort of maybe draw this in for you, right? There's a face which is here, right? There's a face which is this piece here, and then there is a face at the bottom, right? So they're just the three faces, but it's just a two-dimensional cone, if you will. Okay, so you go from that, it's like, and then you can collapse each of those faces, it's like back down to their edges, so you end up with something like this, right? And then once you've done that again, you can sort of, very clearly, it's like pull this back to just the point at the end. Okay, so this is an example of what I mean. It's like by collapsing a simplex, right, to a point. Okay. So more generally, of course, you can apply these elementary collapses to any simplicial complex, right? You can apply elementary collapses to sort of more general simplicial complexes. Say K, all right, and if you let L be the result of the collapse of the collapse, then the point is that each of these collapses, elementary collapses, can be realized as a deformation retraction from one stage to the other. So basically, this then gives you a sequence of deformation retractions, which then retracts the underlying space of K, the underlying space of L. Okay, so these elementary collapses sort of demonstrate that there is a deformation retraction from the underlying space of K to the underlying space of L. Okay, so in particular, this means that K and L have the same homotopy type. So K and L have the same homotopy type. And sort of analogous to, contracting to a point, it's like, and sort of referring to that as being contractible, if you have a complex K, which can be sort of, it's like, for which there's a sequence of elementary collapses so that you end up getting a vertex, right, then we say that K is collapsible. So K is collapsible, right, if there is a sequence of elementary collapses that reduces K to a single vertex. And as we demonstrated, it's like earlier, if you, for example, take it's like a 3 simplex, you can, apply a sequence of elementary collapses so that eventually gets to a single vertex. So it is collapsible. Okay. And it's easy to convince yourself that any top simplex is collapsible to a single vertex. Okay. So since collapse preserves the homotopy type, right? Then we know that this idea of collapsible implies that the space is contractible, right? So K collapsible sort of implies that the underlying space of K, right, is contractible. Okay, but the converse is not necessarily true. Okay, but not every simplicial simplicial complex with a contractible underlying space is collapsible. Okay, so far it's like we've been talking about sort of elementary collapses. It's like from a simplex of dimension k plus 1, it's like to a simplex of dimension k. All right, and as you might expect, you can generalize this idea to sort of simplex pairs which differ by more than one dimension. Okay, so let's sort of state that and then sort of see when that actually is possible. Okay. Okay, so we want to extend sort of the notion of collapse to pairs of simplices. Let's call it tau and nu, right, whose dimensions differ by one or more. Okay, we already did a case where they just differ by one. It's like we want to be able to, it's like have a definition where sort of larger dimensional differences are allowed. Okay, so previously it's like you required that V is the only proper coface, it's like of tau, right? So previously required that, well, nu, I guess, nu is the only proper coface of tau. All right, so now require that all proper cofaces of tau are faces of nu. Okay. All right. So if you do that, it's like then we're still in a situation. It's like where you can do this idea of collapse. Okay. And as you might expect, the idea is to find some sequence. It's like where you are contracting things. So if you have, so let's say that the dimension of tau is k. So let's let k equals the dimension of tau, and L be the dimension of nu, right? Then you get L minus k, choose I, simplices of dimension I plus k, and therefore there are 2 to the L minus k simplices between tau and nu, okay, including the 2 you started with, right? So basically you need 2 to the L minus k minus 1 elementary collapses. And again, it's like, yeah, you can, the point is that you can decompose, it's like this collapse of nu, it's like to tau, it's like into a sequence, it's like of 2 to the L minus k minus 1 elementary collapses. When elementary collapses refer to things where you're just collapsing a simplex of dimension k plus 1 to dimension k, right? Okay, so, and then we refer to this sequence then as a sort of KL collapse. Which is compatible with the notation we had used before. And then since this KL collapse is the composition of, you know, it's like 2 to the L minus k elementary collapses, each of which preserve the homotopy type, this more general notional collapse also preserves the homotopy type. So since this is the composition of elementary collapses, that preserves homotopy type, this more general collapse also preserves homotopy type. Okay. All right. So let me